Howdy y'all, this is Mr. M, and today we're going to be doing some special right triangles. This is actually our special right triangle applications. This is really useful, so why don't we just go ahead and start off the day with a problem. Now, first thing we're going to do is read the problem. I'm not going to read it to you because you guys are in pre-AP pre-cal, and I assume you can read. So I'll give you a minute while I select my tools. Okay, well from this problem we see that we have a lighthouse and a ship. And actually I'm going to do this by hand. Well, I'm going to call this little speck right here my lighthouse. And it says right here that the radar determines that the ship is 2,400 meters from the lighthouse, which I'll call it right there. So the distance between here and here is 2,400 meters. And then at some time later, the ship is measured to be over here, and that would be from here to here. That's 2,650 meters. Now we have two parts to this problem, and the first part is, well, what was the bearing change? So this is actually when I'm going to draw my triangle, because now we can actually see it. And my triangle, which will be right here. So once again, guys, that was, here's the lighthouse, here was the ship at the beginning, and sometime later, here was the other ship. And to relabel, this was 2,400 meters, and this was 2,650. And so guys, they want to know what the angle change was from here to here, and that would be given by this angle right here, which we'll call B. We'll call that B. And remember, angles are given by capital letters. So, what trig function out of the SOHCAHTOA, S-O-H-C-A-H-TOA, is going to help me get that angle? Well, I see that I have the adjacent angle, the adjacent angle and the hypotenuse. So I know that the cosine of B is equal to the adjacent, which would be 2,400 over the hypotenuse, which is 2,650. Now, I don't know what B is, but I know what the ratio of the sides were, so I'm going to use the arc cosine, or cosine to the -1. Remember, this was the second cosine of your triangle. Pardon me, I messed up there. This was the arc cosine, which is second cosine on your guys' calculator. I don't have a calculator pulled up, so I'm going to expect you to do this on your own. It was the arc cosine of 2,400 over 2,650. And when I typed that onto my calculator, I got that was 25 degrees. And that's another thing, you need to make sure that you're in degree mode. So, the angle, the ship's bearing changed 25 degrees. Okay, so now that I've done part A, let's move on to part B. And with part B, they want to know how far did that ship travel, which would be actually side length lowercase b. Now, I have three pieces of information now. I know that this was 25 degrees. Actually, 4, I lied. This is also 90 degrees because this is a right triangle. But I can use another trig function, or I can use Pythagorean theorem, which was a squared plus b squared is equal to c squared, and solving for b, I get that b is equal to the square root of c squared minus a squared. So to write that calculation out for you guys, it's going to be the square root of 2,650 squared minus 2,400 squared. Now when you type that into your calculator, it might behoove you to put these into parentheses, but it really shouldn't matter. It's just something I do. But once you've done your number crunching, you should get 1,123.61 meters. Now, last video, I stressed quite heavily that we always use 3 decimal places. But if we scroll up here to our directions, which are always very important to read, we notice that they want the links to be to the nearest hundredth, and our angles to be to the nearest degree. So once we read our directions like good boys and girls, we realized that we only want 2 decimal places. Okay, let's move on to number 2. Number 2 is a little bit more tricky. I'll give you some time to read it. Okay, so what we have here is we have a person who's 152 centimeters tall, and he's staring at a light post across the channel. And he just, I guess he finds it pretty or something. He's attracted towards the light. Maybe he'll go for a swim. But we didn't know how far he needs to swim to get to that light post, so we need the width of the channel. So the width of the channel is going to be given by that triangle that we see, which I'm going to reproduce down here as a shape, which will be right here. Okay, so there's my triangle, and my distance will be x, or my long leg will be x. We know the height of the man is 152 centimeters. He makes a right angle with the ground because he's standing straight up. He's no slacker. And I know that he is looking downwards at a degree of 7 degrees, but, so it's an angle of depression, and remember, that angle of depression is also this angle of elevation, so this is 7 degrees. And I can use another one of my trig identities, which if we scroll back up here, remember SOHCAHTOA, I was given the opposite, and I want to find the adjacent, so I'm going to use tangent. So remember, the TOA part would be TOA, or tangent is opposite over adjacent. So I know that the tangent of 7 degrees is equal to 152 centimeters over x. Now, after doing some rearranging, I get x is equal to 152 centimeters over the tangent of 7 degrees. So once I've typed that in my calculator, also making sure the fact that I was in degree mode, I get the width of the channel to be 1,237.94 centimeters. And I'm going to rewrite that as 1,237.94 centimeters. Now, of course, I haven't given myself enough room to do part B, so I'm going to give you guys a few seconds to copy that down. Or this would also be a good time to pause the video. So, okay, let's move on to part B. Now with part B, they want to find the height of this lamp post. Now, we can do this one of 2 ways. You can solve 2 right triangles, so it'd be this lower 7-degree triangle, and then do the 12-degree triangle, or we can realize that the man is looking straight ahead, and that from here to here is only 152 centimeters, because apparently the world is flat. Now, this gives me, so the remaining part of this, which we can call y, which I'll translate over here to this triangle, is going to be given by the degree of incline, or sorry, I forgot that word, of 12 degrees, and we know that he is 100, or we know that he was 1,237.94 centimeters away. So what I can do is I can also use tangent again, so I know that the tangent of 12 degrees is equal to y over 1,237.94, and once I solve for y, I get y is equal to 1,237.94 times the tangent of 12, and once you type that into your calculator, you're going to get, actually, I'm sorry, this will give you the height of 152 centimeters. We were solving for this guy right here, my apologies. But if we were to solve for what I had actually set out to do, we would have noticed that we would have gotten that y is equal to the tangent of 12 oops, actually, 0.94. Okay, I'm sorry, I messed up twice. This is not going well for me. My apologies. I know Z's going to give me a hard time in class tomorrow, but we end up getting that 263.13 centimeters. So that would be the second part of that light post. So to get the height of the total light post, I need to add 152 centimeters to that. So the height of the lamppost for part B was 415.13 centimeters, or just over 4 meters tall. Okay. Maybe we'll do better on number 3. On number 3, I have a swimming pool that is 3 feet deep, okay? So we're going to 3 feet deep on the shallow end, and then it gently slants downwards at 12 degrees, okay? So we'll draw a horizontal axis here, and we get a 12-degree angle of depression, and it's 50 meters long. So we have a swimming pool that looks like this, and the length of this dotted line is 50 feet. Okay, and we want to know how deep is it at the deep end, and that would be our total distance of y, with this 3 feet plus however much this goes down. So what I'm going to do is I'm going to break this up into 2 sections. I'm going to call this y sub 1 and y sub 2. And in math, you're going to see a lot of subscripts later on, but we'll get used to them now. So I know that y sub 2 from my SOHCAHTOA is going to be equal to the tangent of 12 degrees times, the tangent of 12 degrees times 50, or the length of the pool. This is just like the canal problem that we had done earlier. So once you type that into your calculator, we get that y sub 2 is 10.63 feet. So that means from here to here is 10.63 feet. Now I know y1 was given to me as 3 feet. So when I add y1 and y2 together, I get that my pool has a deep end of 13.63 feet. That's a fairly deep pool. Okay, so that was a quick problem. Why don't we only got 2 more left. Why don't we move on to number 4? I'll give you a moment to read number 4. Okay, so now we have Penny. So we'll draw Penny. Okay, look at my pretty drawing. There we go. Penny has some hair, purple hair. Penny's a punk rock girl. So Penny stands 12 feet away from a statue. Now my statue, not too pretty. It's a box. So Penny's standing 12 feet away from the statue. So that means this distance right here is 12 feet. And an angle of elevation to the top of the statue, I'll give Penny a line of sight right there, is 30 degrees. So that is 30 degrees. And her angle of depression to the bottom of the statue is 15 degrees. So this right here is 15 degrees. And I'm going to break this up into 2 triangles like I had originally done for question 2, but actually this time we actually do need to do it. So my first triangle, which we'll do the angle of elevation first, is going to be here, and we'll call this my angle of elevation to be 30 degrees. She's 12 feet away, and I want to know how tall this section of the statue is, which once again we will call y1. So y1. Now I'm given 3 pieces of information because I always know that this is a right angle, but I'm not going to use that part. But I know that y1 is going to be the tangent of 30 degrees is equal to y1 over 12, and this will simplify to the fact that y1 is equal to 12 times the tangent of 30. And we know our 30, 60, 90 triangle, so you could do it by hand or you can type it into a calculator. And we get the fact that y1 is equal to 4 square roots of 3, or 6.93. Okay, now with y2, we're going to draw another triangle, and this will be her angle of this will be the angle of depression that she was staring at. So we'll draw that down here. And she was looking downwards at a degree of 15 degrees. So that's this triangle right here. I've taken it and I flipped it. And this is, now we're going to do y2. So here's y2, and she's still only 12 feet away. Now, much like y1, y2 is equal to 12 times the tangent of 15, which is equal to 3.25. And I get the fact that y1 plus y2 is 10.14 feet. So that statue is 10.14 feet tall. Okay guys, last problem. Let's finish this one out with a bang. Now, I'm going to give you a moment to read this thing. It looks like we have a drawbridge that is 60 feet long and 24 feet above water. So let's do some labeling. So we know that from here to here is 24 feet. And I know that the length of the drawbridge from here to here is 60 feet. So not quite drawn to scale, but it works. And we have the angle of elevation to be 33 degrees. So I'll write that out right here. And they want to know how tall is it at the tip of P. So I can draw this triangle right here, and they want this entire height. They want the height from the water to the top of P. So we can break this up once again into a y1 and y2 situation. Now, I'm going to redraw the triangle because I like my own triangles. And we know that this is going to be, our angle of elevation is 33 degrees. And we know the hypotenuse, or the length of the drawbridge, to be 60 feet. So now we need to figure out what trig identity we're going to use to find y1. Now, some of us might think, well, why isn't this bottom leg 60 feet? Because when the drawbridge goes down, it's going to have to be the same length, right? Well, actually, when it goes down, it's going to hit all the way over here. So we have this little teeny distance, which we're going to explore here in a moment. So we'll get to that in part B. Now, so going back to part A, I'm going to use the sine. So I know that the sine of 33 degrees is going to be equal to y over 60, or my opposite over my hypotenuse. So when I solve for y1, I get y1 is equal to 60 times the sine of 33. And when I type that into my calculator, which we learned how to do last lesson, it would be 32.68 feet. So I know that y1 is 32.68 feet. y2 was given to me as 24 feet. So the total distance from the tip of P to the water is going to be 56.68 feet. So that is my answer to part A. Now, I'm going to give you a moment, then I'm going to erase this so I have more room for part B. Okay, guys, let's finish this problem. So I got part B to deal with. Now, part B is asking me, when the drawbridge is open, such as it is in the picture, what is the distance between point P and point Q? So what I have here is the fact that I know that Q is on the other side of the drawbridge, and it's 60 feet away from the this side. But so I'm going to end up drawing my triangle, and I know once again that point P, it happens when the drawbridge has an angle of has an angle of 33 degrees. I know that the drawbridge is 60 feet long, and I want to know how far out, or I want to now. Last time we solved for y, now we're going to solve for x, and I want to know how far out, or x1, how far out is P. So I'm solving for x1, which means that I'm going to use the buddy of sine, cosine, to figure that out. So I know that x1 is going to be equal to cosine of 33 degrees, which is not equals, it's just I'm doing cosine of 33 degrees is equal to x1 over 60. And when I solve for x1, I get 60 times the cosine of 33 degrees. And when I type that into my calculator, I get 50.32. So x1 is 50.32. I know when the drawbridge shuts that I have to be able to drive across anyways. So I know the total distance to be 60. So I know this guy right here to be 60 feet. So that means that the distance between point P and point Q is 60 minus 50.32, which is equal to 9.68 feet. So that is my final answer for part B, and I hope I won $1 million, and I hope you guys understand that reference. Okay, well, it was nice teaching you guys today, and I hope you enjoyed this video. See ya.